In this video, I'm going to talk about introduce the idea of maclaurin series. Let me start by recalling some examples of series. One would be the binomial expansion. Okay, and the other would be the exponential function. Binomial expansion, I'm just going to write out a simple example with, say, 1 plus x to the power of, let me just put in a number like 10. Okay, so that would be, if we expand that, this is what we would get. We would get 1 plus 10x plus 10 times 9 over 2x squared plus 10 times 9 times 8 over 3 factorial x cubed, and so on. Okay, so that's kind of the idea. And for the exponential function, if we write it out in a series, it would look like this, as we have seen in an earlier video. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... Okay. Now, the idea with maclaurin's series is that if we can do this, if you can make a series for say these two functions, for those two functions, which are actually quite different if you think about it, right? 1 plus x power 10 e to the power of x, completely different functions. If we can have series like that, which are kind of useful, because if x is small, then the higher order terms become very small, and we can approximate the function using just a few terms. So it can be very useful. And for exponential function, in fact, you can actually calculate the function for any value of x. It will still converge. Okay, so wouldn't it be nice if we can make a series for any function? So let's say I have any function. Okay, so if I have any function, what does it mean if I want to make a series? That means, let's say it's just fx. Okay, let's say it's just fx, and if you look at the pattern for this series, basically you have a number plus number times x plus number times x squared, and so on. And it's the same for this one. Number plus, okay, no number, but no number means 1. Number times x plus number times x squared, and so on. So that's kind of the pattern with these two series. So if I imagine that, or if I hope that I can make a function like this make a series like this in x squared, and so on for any function, it might look like this. It would be like number plus number times x plus number times x squared plus number times x cubed, and so on. So this would have the same pattern as this and this. Question is, how can we find these numbers? Is there a formula? Can we make a formula for it? So let me start by calling these unknown numbers, if you like, a0, a1, a2, a3, and so on. So indeed there is a formula, and it has been found by maclaurin many years ago. So what I'm going to do now is I'm going to explain how we can actually obtain this series. Now, the way that I'm going to try and motivate the idea is to go back and look at, say, one of these examples. Let me look at this example. Okay, say e to the power of x. So we already know what this series is. Okay, let's try this. Suppose that I pretend that I don't actually know what the numbers are in this series. So I'm going to let the numbers be a0 for the first number, a1 for the next one, a2 x squared plus a3 x cubed, and so on. Okay, so I pretend that I don't actually know what these are, and see if we can think of a way to find these numbers. Let's start with a0. How can I find a0? Just by using this. Okay, well, since this is supposed to be an equation, it's supposed to be true for any value of x. Now, what if I set x to 0? What if I let x be 0? If I let x be 0, all these terms that contain x would become 0. And on the left side, I have e to the power of 0, which is 1. So if I set x to 0, I'll be left with just a0 and e to the power of 0. Because all the other terms that contain x would be 0. So that's a simple thing to do, and it actually gives us this, which is actually telling us the value of a0 already, because e to the power of 0 is 1. So just by setting x to 0, we have actually obtained one of the numbers, the first one, a0. So that looks simple enough. But what about, okay, so we have got a0, but what about a1 then? Well, a1 has an x, so I can't just set x to 0, because then a1 is gone. So what can we do about it? Well, if only we can somehow get rid of the x. Well, one simple way might be, say, to divide both sides by x. Okay, but if I divide this by x, then I'll just get a1 right after dividing this by x. But unfortunately, if I divide all of the right hand side by x, I'll get a0 over x. Okay, and I can't quite set x to 0 like that, because then I get a over 0, and that's not defined. So is there some way of getting rid of this x without causing this problem of a0 dividing by x? Well, actually, there's another way of getting rid of this x. It's by differentiating x. Because if you remember, if you differentiate x, you get 1. And if you differentiate a constant, a0, you get 0. So that might actually work. So let me try that. I just differentiate this whole lot. I differentiate this whole thing. I do a d by dx of this. I'll call this equation 1. Call this equation 2. So I do a d by dx of equation 1. Let's see what we would get. So on the left hand side, differentiate ex gives us ex. Same. And on the right hand side, differentiate a constant gives 0. Differentiate x gives 1, so I'm left with a1 here. Differentiate a2 x squared gives 2a2a. And differentiate that, 3x cubed gives 3x squared. The a3 is still here, and so on. Right, you see, we've got what I wanted. We got this a1 here without any x, and we still have the x in the other terms, and we get 0 for the a0, so I don't have to worry about a0s anymore. So it looks like I can now try my trick again of setting x to 0. So let's try that. If I set x to 0 here, what happens to that? X will become e to the power of 0. That's 0, and a1 is still a1, and then x is 0 here, so this term becomes 0. X is 0, so that term becomes 0. And likewise for all the other terms. Now if you look at this, we have actually now have an answer for a1, because now a1 is equal to e to the power of 0, which is again 1. So we can actually repeat this idea for this value. To find a2, we can imagine just applying the d by dx again to this, and that should, according to the pattern that we have seen, that should give us a2. And then if we differentiate, if we differentiate again, we can get a3, and if we differentiate again, we can get a4, and so on and so on. Okay, so this idea actually gives us a way of finding the series for any function. Okay, so that's what I'm going to do next. So suppose now that I have any function. Okay, so just fx, and I want to somehow find the numbers that give this series a0 plus a1x squared, not squared, just a1x plus a2x squared plus a3x cubed plus dot dot dot. Okay. Now, what I would like to do eventually is to be able to find a formula, a general formula for these coefficients. So it would be nice if I can have such a formula, and this means that I should also think about a general term like a n x to the power of n. I would like a formula for a n in terms of n, so that if I want to find a n for say 10 or 20, I can just put this in a formula and get an answer. Okay, so let's try that pattern. If I set x to 0, I get f0 is equal to a0 plus, and the other terms would be all 0. So that gives us a0 immediately. a0 is just equal to f0. Okay. Now then next, let me differentiate that like I did just now. So that's the first derivative. If I differentiate a0, I get 0. If I differentiate a1x, I get a1. Differentiate x squared, I get 2x. A cubed gives x cubed gives 3x squared, and so on. So xn gives n x to the power of n minus 1. Okay, and if I now set x to 0 here, I get f prime 0. Okay, and that's a 1, and x is 0, so all of the other terms would be 0. So this gives me a formula, if you like, for a1. a1 is just what I get if I differentiate fx and then substitute x equals to 0 into the derivative. Okay, so I have a formula for a1 now. Okay, but I'm still some way from what I want to have, which is a formula for an. So in order to get that formula, let me do this 1 or 2 more times to see if we can find a pattern. Okay. Right. So what do we need to do now? We need to differentiate this a second time. So I differentiated it once here. Okay, now I want to differentiate this. So I get f double prime x. That is the second derivative of the function. So I need to differentiate each of these terms. That's a constant, so that differentiates to 0. But differentiate x gives us 1, so left with 2a2. Differentiate x squared gives 2x. Okay, so I'm just going to write this as 3 times 2. I'm not going to multiply them out for reasons which would become clear in a moment. Okay, so x squared differentiated gives 2x, and the 3 is still, the 3 comes from there, and that's the a3, and so on. Yes, I want to have a term, an expression for that. So if I differentiate that, let's see, differentiate x to the power of n minus 1 gives n minus 1 times x to the power of n minus 2. Okay, so I'll carry down the n here. Differentiate x to the power of n minus 1 gives x and gives n minus 1 times x to the power of n minus 2, and I still have a n here, plus dot dot dot. Okay, if I now set x to 0, I'll get f double prime x plus, okay, that's 0, that's constant, 2a2, that would be 0, and all the other terms would be 0 because they all contain x. And so this gives me a formula for a2. 2a2 is equal to this, so a2 would be half of this. Okay, so a2 is equal to 1 over 2 second derivative. I'm supposed to have set that to 0. It's supposed to be 0. So f double prime of 0. This means that I have to differentiate the function twice and then substitute x equal to 0 inside. Now, you might start noticing a pattern here. You see, when I differentiated this once, I have to bring down the power of n down here. When I differentiate it again, the power of n minus 1 comes down here. If I differentiate this again, the n minus 2 power would come down here. So I start getting n times n minus 1 times n minus 2 and so on. Okay, so in this case, if you look at, say, here, this was x cubed. When I differentiated it once, I get the power of 3 coming down here, and the power of x decreases by 1. I differentiate again to get this. The power of 2 comes down, and then the power of 2 decreases by 1 to x to the power of 1. And then this, if I differentiate this again, the x will become just 1. And I get 3 times 2 times 1 if I differentiate again. So what we are starting to get is something that looks like a factorial. Something that looks like a factorial. So, and you see that every time you differentiate once, the first time you differentiate a0 becomes 0. Second time you differentiate a1 becomes 0. Okay, so the starting terms start disappearing. Okay, a0 has disappeared, a1 has disappeared, and if I keep differentiating, these terms will keep disappearing because the power x will keep decreasing, and when it's gone, when the power of x is gone, then when I differentiate it again, it will become 0. So as the term starts all becoming 0 when I keep differentiating it repeatedly, eventually I would reach this term when the power x of this term comes all the way down to 0, and then all the earlier terms would have differentiated to 0. Okay, so if we actually do that, okay, what we would get is that we need to think about when this would happen. Okay, if I differentiate it once, this comes down, the power of n comes down by 1 to n minus 1. Differentiate this 2 times, I get this. N comes down to n minus 2, and I gain these factors. Okay, so each time the factor that I gain, the first factor was n, second factor was n minus 1, third factor must be n minus 2 if I differentiate that again. And that power will become n minus 3. Okay, so let me now do this for focus on this directly, okay, to get a formula for an. Okay, so if I differentiate this once, I will get certain terms here. Okay, and that, okay, I shan't bother to write this out anymore because I've already done that. I'm just going to focus on this. So if I differentiate this once, I get n a n x to the power of n minus 1. Okay, if I differentiate this again, I'll get n, and this would come down, n minus 1, then a n x n minus 2. If I differentiate this 3 times, I'll get n minus 1, and then that factor comes down, n minus 2, then a n x to the power of n minus 3. Okay, so what happens if I differentiate this n times? So each time I differentiate, the power will come down, and the power would be less than the previous one by 1 unit. Okay, so you can already see a pattern here. I should get n, right, see, if you look at this power here is 1 unit smaller than this. And what happens if I differentiate n times? Now this is the power of n. If I differentiate 1 time, I get n minus 1. If I differentiate 2 times, I get n minus 2. So if I differentiate n times, I get n minus n. I get x to the power of n minus n, which is actually just 1, which is a constant. Okay, an is still there, and that number is 1 unit. If there's a 3 there, that's a 2 here. Okay, so let me just write this as 0 instead. Okay, if I differentiate n times, I'll get x to the power of 0. So this number is 1 unit less than this because this is n minus 2 and this is n minus 3. So an is still here. So if this is 0, then this must be 1. Right? This number here must be 1. So on this side, I still have the n minus 1, n minus 2, and so on. So the numbers here keep decreasing in units of by 1 unit. Right? So n minus 1, n minus 2, and so on until 1. So before 1, there must be a 2, and there must be a 3 before that. So this is what we get. Now if you look at this is actually just n factorial. So this is just n factorial. That's an, and that's just 1. Okay. Now if this has differentiated to 1, then the terms before those must have all differentiated to 0. Because that's already a constant now. Okay, so the terms before that would have become a constant earlier on because they have lower powers. So all those must have already differentiated to 0. Right? All the other earlier terms must have become 0 already. And then I still have the later terms which have powers of x. So those will contain powers of x. Like if this is x to the power of 0, the next one will be x to the power of 1, and so on. So this is what I'll get now after differentiating n times. Now if I now set x to 0, then what I get is this is what I get. I get f of n bracket 0, meaning that I differentiate n times and I substitute x equal to 0 inside. Now all those terms are already 0, and what I get here, because it's x to the power of 0, so there's no x, it's just n factorial an plus, and the later terms would all contain some powers of x. So those would all be 0 because I've set x to 0. And finally, I have a formula for an. Okay, fn0 is equal to n factorial times an. I can just rearrange this. I can just rearrange this to get an is equal to, just divide both sides by n factorial. So 1 over n factorial fn naught. So that's my formula. This is the formula, if you like, for the maclaurin series. Now, so just as an example, I'm going to use this formula and see whether I can get back my exponential function, e to the power x. Okay, so this time I'm going to let me write out that function here, that formula here. So what I've obtained just now is that an is equal to 1 over n factorial times f n, meaning the function f differentiated n times bracket 0 with 0 substituted into this n derivative of f. So can I use this to find e to the power of x? So let fx be e to the power of x. Let's see what we get. So I need to find some derivatives just to make a few terms of the series to see if they look correct. So let me differentiate this once for a start. And with the exponential function, it's really easy because it will just get back ex all the time. So if I differentiate twice, I still get EX. Differentiate 3 times, I still get EX. And so on. And if I differentiate n times, I will still get EX. Okay, so that's really simple. Now, if I now need to set to find AN. So let me start by finding A0. A0, okay, A0 is equal to 1 over 0 factorial F0 of 0. If I just substitute n into here. Now it looks a bit odd with 0 factorial and F0. What it just means is 0 factorial is 1. Okay, F0 just means that I differentiate 0 times, which just means that we are talking about the original function. So if I substitute 0 into here, I get e to the power of 0, which is just 1. So that's A0. Now, how about A1? A1, the next term. So A1 would be, let me substitute 1 into the formula here. Get 1 over 1 factorial F10. So this means, so that's 1, and this means I differentiate the function once, it's still EX. And I substitute 0 into the X here, which is the same as before, so I get 1 again. Okay, so it's simple enough. And A2, I get I'll just put in the 2 there and there, so I get 1 over 2 factorial F2, 0. So that's the same as the double prime here. 0, I put in 0 into the EX here, and that's again 1. Oh no, that's not 1. That is 1, but I have 1 over 2 factorial. So 1 over 2 factorial times 1. So if I keep going, okay, let me just do one more. A3 would be, just put a 3 in there and there. 1 over 3 factorial F, differentiate 3 times, put 0 into the X. Okay, and again, it's just e to the power of 0, which is 1. So 1 over 3 factorial times 1. So that's what we're going to get. If I now substitute these numbers into the A0, A1, A2, and so on for the function e to the power of x, right, where fx is e to the power of x, let's see what we get. So e to the power of x, A0 is 1, A1 is 1, so 1x, A2 is 1 over 2 factorial, so plus 1 over 2 factorial times x squared, plus A3 is 1 over 3 factorial times x cubed, plus dot dot dot. And this is exactly the series that we know for e to the power x. So it works.